This is going to be a video for 6.6. This is just a section from your book that we pulled out to put in your notes because it's kind of important that you're familiar with these different phrases and know that they all mean the same thing, okay? So a real number r is a root of the polynomial if p of r equals 0. That's what that should say. Okay? Sorry, I'm getting ahead of myself. Here's p of r equals 0. So by saying it's a root, that's what that means. R is also an x-intercept of the graph. X minus r is a factor. When you divide the rule for p of x by x minus r, the remainder will be 0. And r is a 0. So all of those are saying the same thing, okay? So we just need to be familiar with that language and know that it's all asking for the same thing. Okay, so one thing, we're asked to write a polynomial function with these zeros. So the easiest way to write it is in factored form. So we're going to start with, if these are zeros, then their factors are their opposites, right, with x. So if negative 2 is a 0, then x plus 2 is a factor. If 2 is a 0, then x minus 2 is a factor, as well as x minus 4. So here is a polynomial that satisfies that, okay? And we can distribute it out to put it in standard form as well. So this is difference of squares, so backwards would be this, right? And then I can distribute here, so x squared times x is x cubed, minus 4x squared, minus 4x, plus 16. So that would be our polynomial function in standard form. Okay? All right, so revisiting the fundamental theorem of algebra, remember that the degree tells us how many zeros there are. Now, something we haven't seen yet is that we can actually have complex zeros, okay? These ones will not be shown on the graph, okay? So, real or imaginary, right, is what is included in complex numbers, and the imaginaries are not seen on the graph. Okay? And that includes multiplicities. So if a root occurs more than once, we count that multiple times to add up to whatever degree it is that we're looking at. So just like with radicals, irrational roots, how we had to have the conjugate pair, the same is true for complex roots. So if we have a imaginary root, then its conjugate is also a root. Okay, so we're going to see an example of that here. All right, so first, we're going to solve like we've been doing. We're going to use graphing technology to see if we can get some nice zeros from the graph. So right away, I notice this is a fourth degree, so I should have 4 roots. Okay, so here's the graph. You can zoom out to see all of it if you want. Okay, well, from the graph, I am getting 2 nice zeros, okay? Negative 2 and 1. All right, so that's still helpful. So from graph, we got x equals negative 2 and 1. It was crossing through at both of those, so they only had a multiplicity of 1. So what that means, if we're not seeing it any other points where the graph is crossing, is that my other 2 roots are going to be imaginary. So how do we get those? How do we find out what those are? Well, we're going to do the same thing we did before. We're going to use these zeros and divide them out using synthetic division. All right, so we'll start with negative 2. Sorry, I made a mistake somewhere. Negative 1. Oh, right there. 2 plus 2 is not 0, it's 4. Negative 2 times 4, negative 8. There we go. So we know we should get a remainder of 0. Now I'm going to divide out the 1. Bring down. Add. All right, so we went from a 4th degree to a third degree. So now this is a quadratic. So I have x squared plus 4 equals 0 remaining. So now if I solve this, I can use the square root property. Now taking the square root of a negative, right, I know that that's going to include I. So square root of negative 1 is I, square root of 4 is 2, so this is x equals plus or minus 2i. And there I see the conjugate pair again, the positive and the negative. And that accounts for my 2 missing roots. So zeros for this graph are negative 2, 1, and plus or minus 2i. So I still have 4 roots. Only 2 of them are visible, and that's because they are real roots. They're real numbers that I got. If they're imaginary, we won't see them crossing the x-axis, but they still exist. So we still want to be able to find those. All right, x to the 4th plus 7x squared plus 12. So let's switch the graphs here. All right, well, this one doesn't cross the x-axis at all. So it means all 4 of my roots are imaginary. So again, how do we get those? Well, if I can't divide any of them out, because there's nothing nice on the graph, we are going to try and factor. So this kind of has the form of a trinomial. Instead of x, I'm going to use x squared in my factors. But numbers that multiply to be 12, that add up to be 7, are 3 and 4. So I'm going to write it as x squared plus 3 and x squared plus 4. So then I get the x to the 4th when I multiply those. All right, so now once it's factored, we set each factor equal to 0 and solve. So again, I'm going to get negative numbers here. Well, we saw this one already, x squared equals negative 4. When I take the square root, I get x equals plus or minus 2i. Here, when I take the square root of negative 3, I get I and then root 3, right? 3 isn't something nice that I can take the square root of, so there's my 4 roots. 1, 2 here, 3, 4 here. So zeros are plus or minus I root 3 and plus or minus 2i. Again, I'm seeing those conjugate pairs. Anytime I have imaginary, I have the plus and minus there. Okay, so now we are kind of doing the opposite. We're going to be given some information about a polynomial and trying to write the equation for it. Okay, so I know it's a third degree, so I should have 3 zeros. Well, nicely, they're giving me all 3. And then they're actually giving me a point that this graph must go through. So I'll talk about how to deal with that in just a second. So let's write it in factored form. That's the easiest way. So we have a function x plus 1, x minus 2, x minus 4. Okay, so this is saying p of 0 must equal 24. So a lot of times we have a leading coefficient. It's hard to see when it's in factored form, okay? So if you want, you can go ahead and distribute this out. So I'm going to go ahead and do that. I'm going to start with these first 2. I have, actually no, I'm going to leave it like that, you guys, for right now. Okay, but this leading coefficient, I don't know what it is right now, but it has to make this part true, that when I plug in 0, I get out 24. So we're going to do that. So we're going to plug in 0 for every single x, and we're going to solve for that a value. So 0 plus 1, 0 minus 2, 0 minus 4. Order of operations, do all the parentheses first. So I have a times 1 times negative 2 times negative 4 equals 24 is what we want it to equal. Okay? And negative 2 times negative 4 is 8, so we have 24 equals 8 times a, divide by 8, so a must be 3. So my function is 3 times x plus 1, x minus 2, x minus 4. Okay, and again, typically we would want that in standard form, so I'm going to distribute these guys together first. So we have, let's see, x squared minus x minus 2. Oh, and I still have the 3 there. Okay, multiply these guys. I'm leaving my 3 out front right now. So I have x squared times x squared times -4, negative x squared plus 4x minus 2x plus 8. Combine some like terms. X cubed minus 5x squared plus 2x plus 8, all multiplied by 3. 3x to the third minus 15x squared plus 6x plus 24. So this is a polynomial that has these 3 zeros. It's of degree 3, and when we plug in 0, we get 24. All right, we got another one like that. Okay, here, also degree 3, they're only giving me 2 zeros though. And then again, I'm going to solve for a leading coefficient. So I know there should be 3 zeros. So because this one is imaginary, I know that negative 3i is also a 0, right? Anytime I have an imaginary root, its conjugate is also a root. So there's my 3 zeros. So I'm going to write it in factored form. So I have x plus 6, x minus 3i, and x plus 3i. Now, for this one, you guys, I am fine with you leaving it in factored form as long as there are no i's. So what that means is at least distribute this piece so that the i's go away here. So remember, this is difference of squares. So this becomes x squared minus 3i squared. Okay, well 3i squared is 9 times -1, so this becomes -9. X squared minus 9 is x squared plus 9, excuse me. So you can distribute this out more if you want. I'm fine with you leaving it in this form, okay? So here is my function, but again, I need to find a so that this is true. So I'm going to plug in 0, and it needs to equal -108. So we got 0 here, so I'm going to be left with 6, 0 here, left with 9. Okay, so we get 54, -108 divided by 54 is 2. Sorry, I'll write that out. So a is -2. So my function then, completely with the leading coefficient, -2, x plus 6, x squared plus 9. This has those 3 zeros. It's a third degree. And when we plug in 0, we get -108. Now, how do you know it's a third degree here? Well, if we were to distribute, the most I would get is x times x squared, which is x cubed. All right, last one here, you guys. One more example like this. Okay, one possible polynomial from the function. So they are not giving me a point that it has to go through, so we're not going to worry about a, that leading coefficient. We are just going to write out all the zeros. So that's an imaginary 0. That's a radical, irrational 0 with a radical. So their conjugates are also zeros. So here's the other zeros. 1 minus I and -√2. Okay, so this one is actually going to be a fifth degree. So let's write out our thing in factor form. So x minus this root, 1 plus I, x minus this root, okay, and then x plus √2, x minus √2, and then x plus 1. Whew, okay, so let's see here. I'm going to we want to, again, at least distribute enough so there's no radicals and no i's. So the radicals, if I multiply those together, again, that's a difference of squares. So I get x squared plus, or excuse me, minus √2 squared, which is 2. So x squared minus 2 is what that part turns into. This one is a little interesting because the complex number has two terms. I'm actually going to distribute this -1 here. So I get x minus 1 minus I. Same thing on this one. I get x minus 1 plus I. Okay, so when I distribute this guy out, I get x times x times -1, x times I, -1 times x, -1 times -1, -1 times I. Okay, now I have -I times everything, so negative xi plus I, and then minus I squared. Okay, so what's going on here? Well, I get some stuff to cancel. Positive xi, negative xi, negative I, positive I squared is -1, so minus -1 becomes +1. Negative x is -2x, so 1 plus 1 is 2. So that whole thing, when it's distributed out, becomes this. There's no i's anymore, so I am fine if that's as far as you go. And then there's our other 3 groups there. And then I'll put equals f of x or p of x, whatever you guys want to use. All right, okay, that is it for this video. Thanks for watching.